So let's do an example problem. Let's imagine a spacecraft traveling off to another star. So we've got a spacecraft here, and it's traveling off to another star, and or even just traveling around in a big circle, and then comes back to the starting point. And so we have one person standing here on Earth, waiting for the spacecraft to come back. And the spacecraft, let's say, is going at a velocity of 0.95 the speed of light, so 95% the speed of light. And so it travels for a time of 7 years for the person on board the spacecraft. And so the question is, therefore, in that case, how much time has elapsed for the person still back here on Earth? Okay, and so we know that that time is going to be gamma times T naught. Gamma is 1 over square root 1 minus V over C squared. So that's going to be 1 over square root 1 minus 0.95 C over C squared. So those C's cancel. So gamma is going to be 1 over square root 1 minus 0.95 squared. And so that's going to come out to be 3.20. Therefore, T is going to be 3.20 times 7 years. So T is going to be 22.4 years. Okay, and so that means that the spacecraft here, so the spacecraft has gone off and circled around, and on board the spacecraft 7 years pass, but back here stationary 24 years have passed. So in other words, if you're on the spacecraft, you're only 7 years older, but if you stayed home, you're 22.4 years older. And so you experience this difference right here of time. And so this is the essence of how this sort of thing works. Now, interesting thing about this is that it also gives rise to another very interesting problem, and that is the whole idea of what does time passage mean. Because we got two observers and they're both experiencing time passing. Each of them feels like time is passing normally for them. So in other words, the observer standing put, seeing the other person moving, the astronaut moving, looks like they're moving slowly. In other words, if they speak, it's going to be almost as if they were speaking in slow motion, 3 times slower. So in other words, if you want to hear the conversation normally, you'd have to speed it up by a factor of 3.2. Whereas for the person that's moving, if they get a signal from home, then it's going to be high speed, and they got to slow it down by a factor of 3.2. So in other words, for the moving observer, it appears as if that things are running extra fast for everybody else, and for everybody else, it looks like the moving observer is running extra slow. Now, this becomes very problematic in trying to figure out who's actually moving, because remember, they're trying to measure relative to something, and so that does make it a little bit difficult to figure out who's the one that's actually moving, because everything in the universe moves. So that gets a little beyond the level of this class. But here's the other interesting thing. Okay, for the one that was moving, they went for 7 years, and they went for 7 years at a velocity of 0.95 the speed of light. So that means they went a distance of 6.65 light years. Okay, so that's the distance they travel. But for the stationary observer, watching the whole thing, they saw the velocity at 0.95, the speed of light, but they saw it go for 22.4 years. That means they found a distance of 21.3 light years. Okay, so now we have yet another problem, and that is the moving observer thinks they only went about 6 2/3 light years. A light year is the distance that light travels in 1 year. So that's about 6 trillion miles. So the moving observer thinks they only went 6 2/3 light years, whereas the stationary observer saw them go about 21 1/3 light years. Okay, so now we have a discontinuity between the measures of distance involved here. Okay, so that's going to bring up our next topic, and that is what we call length contraction. The faster you go, space is also distorted.